All right, so an important component of solving equilibrium problems, when we get to that, is using an equilibrium expression. So an equilibrium expression relates products and reactants in, much like a rate law, an expression that includes an equilibrium constant. So why don't we look at that now? And so here's our generic equilibrium. A plus B yields C plus D with the stoichiometry in lowercase. And so we can write a rate law for the forward reaction. So rate forward equals K forward times concentration A raised to the power of A times the concentration of B raised to the power of B. And so that refers to the rate of the forward reaction. And so the reverse reaction also has a rate, and that's going to be our I'll say B for backwards equals rate constant B times concentration C raised to the power of C, concentration of D raised to the power of D. And so we have these two different rate expressions. Well, at equilibrium, rates are equal. So if you have that double error, it means those two rates, the rate of forward reaction and rate of the back reaction, are equal. And so if they're equal, we can say that KF A B equals KB C D. I think you know where I'm going here. And so if we isolate the concentrations, this is typically what we end up doing. We end up with this an expression like this: K. It's going to be KF over KB equals C D over A B. And this expression, the K expression, that's a constant divided by constant, so it's actually just one big constant, and we call that the equilibrium constant uppercase K. Make note of that, it's uppercase, and the lowercase c just stands for based on concentration. And so that is how we arrive at an equilibrium expression. Excuse me. One thing to note is, I mean, I have C D over AB, so I have products over reactants. I could have reactants over products. It would just mean I would have a different equilibrium constant. So this is the convention, and so I'll show you the convention right now. By convention, it is products over reactants. So you can see that there. Products, concentration of products over concentration of reactants in your equilibrium expression. So that's why you have C over CD over AB. So there's my equilibrium constant, uppercase K and lowercase c. Now, lowercase c could also be EQ, so subscript EQ, which stands for equilibrium constant, so a constant at equilibrium. You will also see it as Ka, and that's an acid dissociation constant. You'll see Kb, that's a base dissociation constant, and you'll see Ksp, and that's a solubility product constant. So we're going to come across all of those. And one other one you're going to see, and we'll see this in a minute, is Kp, and that's an equilibrium constant based on pressure. Anyway, so you're going to come across those other types of equilibrium constants as we proceed in this unit. So square brackets obviously refer to concentration, and that's the case for all of these with the exception of Kp, and we'll see why in a minute. As it says, the products over reactants, and the indices, or those stoichiometric coefficients. The exponents here, the indices, are derived from the stoichiometric coefficients from your balanced equation. So writing an equilibrium expression is really not that hard once you have an equation in front of you. So here's an example. This is the Haber process, the production of ammonia gas. And so we can write an equilibrium expression, Kc equals, and so products, ammonia, NH3, concentration, and there's the 2 in front of it, so it becomes raised to the power of 2, nitrogen gas, and 2, and hydrogen gas, H2 raised to the power of 3. And so it's the product of. So product of, there's only one reactant, or only one product. There's 2 reactants, so the product of the concentration of those reactants. So that's an equilibrium expression. A couple more examples. So here's the equilibrium for either the decomposition or dehydration of a ester. So you might remember this from organic chem. So again, K, I'm going to use the expression EQ here. It just means equilibrium, at equilibrium, equals products. So CH3COOH, if you remember what that is ethanoic acid. And CH3CH2OH, that is ethanol. Products over, and so what we have here is CH3, COO, CH2CH3, that's the ester, that's ethyl ethanoate, and water. And I did mention this when we did this reaction in class. This is an equilibrium situation, double arrow indicates that. And so this is why if you're trying to produce your ester, you have to draw off the water, otherwise you reach an equilibrium. And when you're in equilibrium, water reacts with the ester you're trying to collect to go back and form your carboxylic acid and your alcohol. So formation of esters becomes an equilibrium. If you want to collect your ester, you got to get rid of the water. Final example, SO2 plus O2 yields SO3. Now hopefully you recognize this is not balanced. A couple of reasons why we might recognize that. First one is the spaces in front of these things. So we're going to have to balance this. So let's balance this equation. We got sulfur is balanced, but oxygen is not. We have 4 and we have 3, so we're going to multiply that by 2, and we're going to multiply that by 2. Oops, we're not going to multiply that by 2. We're going to multiply this by 2. And so we have 2 times sulfur, 2 times sulfur, 2, 4 times, sorry, 4, 6 times oxygen, 6 times oxygen. So now it's balanced. So just to remind you that you have to have a balanced equation. But now we can write our equilibrium expression, SO3 squared divided by SO2 squared O2. And so there's the equilibrium expression for that reaction. And so writing equilibrium expressions, you get quite a lot of practices. You should be pretty good at it. It's not that difficult. Don't forget to write it. Don't forget to write an equilibrium expression in terms of the equation first, the balanced chemical equation. You'll then do substitution once we start adding numbers to these problems. And that concludes this video.